And thank you to the organizers for inviting me and for putting this whole conference together. It's great to have so many graduate students here. I have the impression that this is kind of a broad audience, so I wanted to give a pretty introductory talk, kind of about some basic ideas in geometric group theory. So the talk is about hyperbolic geometry and group extension. So what I'll do is focus for a while just on the idea of hyperbolic groups, which is some sort of important concepts in geometric group theory. I'll try to give the definitions and convince you maybe that's sort of an interesting topic to study that you might care about. And then we'll change gears a little bit and explore that idea in the context of group extensions and sort of ask, when could a group extension be hyperbolic? Okay, so let's get started. So we want to study in geometric group theory, it's kind of a geometric group theory talk, so we want to study groups as geometric objects. Okay, so that's the basic idea. So how would you do that? Well, maybe there's different things you could do, but here's one thing you could do. Let's say that G is a finally generated group. Okay, let's say that we have S, a finite generating set, and let's assume it's a symmetric generating set. So, S is equal to S inverse. Okay, so then I could build the Cayley graph. GS. Okay, so what is that? That's just a simplicial graph. Okay, so it consists of vertices and edges, so I'll tell you what they are. So the vertex set is just your group G. So every element of your group is a vertex. And then I have an edge connecting two vertices if and only if I have A is equal to BS for some thing in the generating set. And that's symmetric because it's a symmetric generating set. So you could switch A and B and it's the same thing. All right, so that's some graph. OK, so then I now have this simplicial graph, and I could give it the path metric. Oh, and I want to call this, I'm going to call it X. OK, so X is the simplicial, is the Cayley graph. OK, and I have a path metric, D on X. OK, so I just have 2 points. The Cayley graph, the distance between them is you try to find the shortest path. Okay, edges have length 1 by convention. All right, so that's a metric on this space. And the group G acts on X isometrically, sort of on the left. It's a left action. Okay, so the normal action of the group on its own vertices by left multiplication extends to an action on this Cayley graph. It's a simplicial action, so you get an isometry with respect to this metric. OK, so great. So I started with the group. I chose a finite generating set. I built this metric space. G is a subset of X. It's just a set of vertices, right? So I get an induced metric on G because it's just a subset of X. OK, so it's the restricted path metric. All right, so now I've taken my group and I've turned it into a metric space. OK, and this is called the word metric. It's called the word metric because the distance from the identity element to G, if you work it out, is just the length of the shortest word in my generating set that represents my element G. Okay, so that's great. Now there's sort of a problem with this story is that I had to make a choice somewhere, right? I chose S, and it's pretty easy to see that if I choose a different S, I get a new generating set S with S prime here. The Cayley graph will be totally different, okay? And the metric that I get induced on G will be a different metric. Okay, so I don't really have a well-defined geometry on my group, so that's a little unfortunate. So you work around that in the following way. Okay, so let's see. Clearly, X depends on S. Okay, so let me make a definition. We said the metric spaces X and Y are said to be quasi-isometric okay, if there exists a number k greater than 1 and a map from X to Y with the following property, two properties. Okay, so first of all, if I take two things in X and I apply f to them, and I measure the distance in Y, that's in Y, well, that should be sort of controlled in terms of the distance in X. Okay, so you might hope for this. So that would be, of course, they would all be equal, and that would be an isometry. So a quasi-isometry is just where I have this, but I allow myself some wiggle room with multiplicative and additive error. So I divide by k here, and I subtract k, and I multiply by k, and I add k. This is for all a and b and x. Okay? So that's the definition of what's called a quasi-symmetric embedding. If you just have that, so just this part here is a QI embedding. Okay, to be a quasi-isometry, there's an additional condition, which is that the image is sort of almost everything in Y. So I say is K dense in Y. Yeah, please.
So this isn't quite by ellipses. Is it critical that you have minus and plus K?
For certain things, yes, and for other things, no. Okay, so that's a good question if you anticipate what I'm about to say next, which is that if I change my generating set like this, I change S to a new generating set, I'll have two graphs. Those graphs turn out to be quasi-symmetric to each other. In fact, it's an exercise, they're actually by Lipschitz to each other, which is if I delete this K here. I just have multiplicative error. So that's an example of quasi-isometry. But in general, we like to allow this sort of more general sort of thing. Okay, so let me write that down. I guess the thing I just said. It's an exercise. Any two Cayley graphs for G are quasi-symmetric. Okay, and in fact by Lipschitz to each other. Okay, so what that means for us is we don't have a well-defined geometry on our group, perhaps, but if we have geometric ideas or sort of properties that are invariant under quasi-isometries, then it makes sense to talk about whether or not my group has that property. So if you have a geometric property that's preserved under a quasi-isometry, then you could ask whether or not your group has that. It's a well-defined question to ask. Okay, so this is sort of the context of geometric group theory, is to study finally generated groups up to quasi-isometry like this. Okay, so what sort of invariants or properties might you like to consider? So one of them that I want to focus on today is the idea of hyperbolicity, or Gromov hyperbolicity. So let me define that. A geodesic metric space X. So by a geodesic metric space, I just mean a usual metric space with the property that any 2 points can be joined by a geodesic. So for example, a Cayley graph is or anything with a path metric on it like that is a good example. So a geodesic metric space is, I'll call Gromov hyperbolic. I'll usually won't say Gromov. Hyperbolic if the following thing happens. So if there exists some number delta greater than 0 such that every geodesic triangle in X is delta thin. Okay, delta thin just means that each side of the triangle is contained in the delta neighborhood of the other two. Each side is in the delta neighborhood of the other two. Okay, so there's an obligatory picture here that I draw. So here's a picture of a triangle. Okay, so triangle is you just pick 3 points and you choose geodesic segments between them. So then I'll pick a side, the bottom side, and I wonder, is it contained in the delta neighborhood of the other two? So I draw the delta neighborhood of this thing and of that thing, and I shade them in, and I ask, is this side contained in that? And I guess here I failed because I'm bad at drawing the picture. So it's not. Okay, but if it was contained, then it would be, for every triangle, it would be delta hyperbolic. Okay, so that's delta hyperbolic. All right, so that's a weird property, perhaps, but it turns out to be very useful for this topic. Oh, you have a question?
So does this imply that any 2 points are within delta of each other, so your space has a finite radius?
Oh, no. I'll do some examples.
Draw a picture that looks like you're taking the union of those two sides, but your words are saying you're taking the intersection.
I meant the union. Yeah. So all right. So I'll try to say it again. So triangle's delta thin is if I take two of the sides, I take the union of their delta neighborhoods, and I ask if that union contains the third side.
Okay.
That's the condition. Yeah. Okay. And if that holds for every triangle with the same number delta, every triangle is delta thin for some delta. I want it to be a uniform delta for all triangles is the point. Okay. Then I call the space Gromov hyperbolic. Okay, so let's do some examples. One is a tree. Okay, here's my picture of a tree. Etc. Okay, so a tree like that, a graph with no loops in it. And all right, we have to check this condition. Is it Gromov hyperbolic? All right, you pick 3 points. Where do maybe you pick that point, and this point, say, and I draw a geodesic triangle between them. Okay, so that looks like this. That's one side. Here's another side, and the third side is like this. Those are geodesics between those 3 points. Each side is in fact contained in the union of the other two sides. So it's contained in the zero neighborhood of the union of the two sides. So it's zero hyperbolic. Okay, so tree, this is zero hyperbolic. Okay, is that clear? Okay, great. 2 is the hyperbolic plane. H2. Okay, so this is, I'm not going to define what the metric on the hyperbolic plane is. It's the upper half plane with the usual Euclidean metric, but scaled by 1 over y as you go up, okay, or the Poincaré disk with the usual metric on it. Okay, I want to show you, all right, it's called the hyperbolic plane. You would hope it's hyperbolic in this sense. That would be really unfortunate if it wasn't. So let me try to convince you it satisfies this definition. Okay, here are 2 facts about it. Every geodesic triangle in H2 has area. Maybe you know. What's the area of a geodesic triangle in the hyperbolic plane? It's at most pi, right? Every triangle has area at most pi. Okay, so that's some basic facts about the hyperbolic plane. And then here's another fact. As you can calculate the area of a circle of radius, or let me say a disk of radius r. Anyway, this people don't always know. I have to look it up. All right, it's 2 pi cosine, hyperbolic cosine of r minus 1. Okay, that's bigger than 2 pi if r is 2, say. Okay, it gets big. All right, that's the whole point. All right, so now I draw a triangle. Here we go. All right, that's a geodesic triangle. And I'm trying to check if this side is contained in the union of the other two. So I go here. Let me draw a ball. This is ball of radius 2. 2, centered at a point on this geodesic. Well, the geodesic cuts the ball in half. Okay, so the inside of the triangle has half the area. So how much area is that? Well, the total area is more than 2 pi, so the half on the inside is pi. The area of the triangle is only pi. So the half of the ball that's on this side is bigger than the area of the triangle. So it can't live in the triangle. So it has to be bigger than that, actually. It has to look like that and touch the other sides, one of the other two sides. Well, that means this point is within 2 of a point right there. Okay, so it's thin. Is that clear? All right, so hyperbolic plane is Gromov hyperbolic. That's good. Okay, so those are 2 examples. And then important fact for us is that this property is invariant under quasi-isometries. Okay, so that's something you're just going to have to believe me about. I'm not going to give the proof, but it's a good exercise or thing to look up if you've never thought about before. I think it's kind of fun. But yeah, it turns out if you have one metric space in this situation here, if x is hyperbolic and you have a quasi-isometry, then y will also be hyperbolic with a different delta, perhaps. So hyperbolic means there is some delta. Okay, the upshot for us is that we can define a group G is hyperbolic if any of its Cayley graphs are hyperbolic. Okay, that's a well-defined definition, right? I have my group, I pick any finite generating set. It's a finitely generated group. Of course, I look at the Cayley graph, I ask this question, if it's hyperbolic, then if you choose your favorite generating set, it will also be hyperbolic because of this fact. Okay? Any questions? Yeah?
I have a question if we go a little back. So in your definition of Gromov hyperbolic, there exists a delta such that that happens?
Yes.
But can you give me a case where that doesn't? So you have a finite number of triangles.
Oh, yeah, I should give you a non-example. Yeah. You just want a non-example? Okay, that's a good, I should have done that. Thank you. Okay. There we go. Okay, here we go. Non-example is, say, R2. Let's even easier. Let's say Z2. Okay, so it's this Cayley graph of Z2 is the grid. Well, it has different Cayley graphs, but let's do the usual thing, the Cayley graph of Z2. All right, so now I'll show you triangles that are not delta thin. So, and you know, for whatever deltas, you pick a delta, whatever delta you pick a million. And I draw this picture really big, bigger than a million. There's one side, there's another side, and there's the third side. Okay, and I can make that picture as big as I want, so it's not hyperbolic with any delta. Okay, very good. Any other questions? Yeah.
Why the ball of radius 2 crosses both of the other two sides?
It doesn't have to cross both.
But this point should be the...
It just has to cross at least one of them, which is all I care about. Yeah. Okay, good. Any other questions? Yeah. Oh. All finite groups are delta hyperbolic. That's a good observation. Yes, because I just take delta to be bigger than the diameter of the Cayley graph. Great. Okay. So we did that. So let's, we had examples of hyperbolic. Huh?
Can I add an obnoxious one? Can you give an example from differential geometry?
Example from differential geometry. R2 with the, oh, an actual example.
A class of examples.
hyperbolic plane, you mean like that? Hyperbolic end space? I don't know what you're hinting at.
Negatively curved manifolds.
Negatively curved manifold. We're getting there. Okay, so we defined a hyperbolic group. I want to give some examples of that. So one is a free group. Right, the free group on two generators, its Cayley graph is a tree. Trees we just saw were delta hyperbolic, so free groups are Gromov hyperbolic. Okay, good. Two surface groups. Pi 1 of SG, where this is a closed surface of genus G at least 2. Okay, not for genus equal to 1, because then it's Z2, and we already saw that that was not hyperbolic. Okay, so why is this true? Well, let me see if I can convince you briefly. So you can give SG a hyperbolic metric, a hyperbolic Riemannian metric on it. And then if I do that, then the universal cover is isometric to the hyperbolic plane. Okay, I guess that's what I mean. Yeah.
I'm being really slow here, I'm sorry, but Z2 is free, isn't it?
So Z2 is a free abelian group. I mean a free, just normal free group. Free group on two generators with no relations.
Yeah, it's just, you said these are examples of hyperbolic groups?
These are examples of hyperbolic groups. Yeah.
And you said Z2 is not, I'm sorry.
Z2 is not a free group. It's a free abelian group, which I don't count as a free group.
Okay. All right. Okay, got it. Now I see what you're saying.
Okay, so if I give my surface a hyperbolic metric, then if I look at the universal cover, I can pull back that metric, and that will be something that's isometric to the hyperbolic plane. Okay, that's what it means to have a hyperbolic metric on it. Okay, and my fundamental group of my surface acts on the universal cover, so it acts on H2 by deck transformations, and since I just pulled back a metric, this will be by isometries of H2. So this action, so now my group will be acting on H2 by isometries. And the quotient is compact, it's just my surface. And it's a basic fact in geometric group theory that if you have a group acting in sort of an isometrically hyperbolic space with a compact quotient, you need a properly discontinuous action, then the group is isometric to this, is quasi-isometric to the space. Okay, so this group, if you give it, the Cayley graph metric or whatever, will be quasi-isometric to H2, which is Gromov hyperbolic, so the Cayley graph will be Gromov hyperbolic. Okay, so this is sort of, I'll just write that out. It's called the Milnor-Svark lemma, which I don't know how to. There's different options for spelling that, so I'll just choose some combination of them. That your fundamental group is quasi-isometric to H2, so therefore this is a Gromov hyperbolic space, so this is a Gromov hyperbolic group. Okay? All right. Okay, so those two examples. And you could do the same thing as Dave was suggesting. You take any, say, closed negatively curved manifold, its universal cover, will be a hyperbolic space. The fundamental group will be quasi-isometric to it and will be a hyperbolic group. Okay. Okay. Oh, and then one more. Let me just put it down here. Fact containing Z plus Z is an obstruction to hyperbolicity. Okay, so we saw that Z plus Z is not a hyperbolic group, but in fact, any group that contains Z plus Z as a subgroup can't be hyperbolic. It's like anathema to hyperbolicity. Okay, so that's one way to rule out being hyperbolic. Okay, so that's some examples of this property, and you might wonder, okay, great. but why would you care about this? What's it good for? What will it, how does it help you actually understand groups? Okay, so I want to give you a few consequences of this before we turn our attention to group extensions. Okay, so let me start the consequences with a definition. An L local geodesic and X, again, X will be my geodesic metric space, is a map from some interval, maybe A, B, into X. So it's a map like that, such that the restriction is a geodesic for every subinterval I with length of I at most L. Okay, so again, an L local geodesic is just a map. Like a geodesic is usually a map of an interval into your space. That's an isometry on the whole thing. Okay, so a local geodesic is a map like that, but anytime I restrict to an interval of length at most L, then that itself is a geodesic, but the whole thing might not be. Okay, does that make sense? So an example, or a non-example, would be in the sphere, S2. Okay. Okay, by geodesic I mean, is a isometric map from the interval n. So look at this path here from the South Pole, maybe down to that point there. Okay, so that is like a pi local geodesic. If I restrict any subinterval of length pi, like from here to here, this is the shortest path between those 2 points, or it's the shortest path between these 2 points. But it's not the shortest path between these 2 points. It's not a global geodesic, but it's a local geodesic. Okay, so that's a non-example.
Doesn't that make it an example?
Is it what?
It's an example of a local geodesic.
It's an example. Oh, sorry. It's an example. Yeah, thank you. Thank you. Okay, good. It's a local geodesic. Okay, so what's a great thing about hyperbolicity is that local geodesics are actually kind of like geodesics globally. Okay, so here's a fact. Given delta, there exists K and L such that if X is delta hyperbolic, I guess I didn't define that. That means triangles are delta thin. Okay, and gamma is an L local geodesic, then what do I want to say? Gamma of the distance between gamma S and gamma T is at least as big as 1 over K S minus T minus K for all S and T. Yeah?
Is every local geodesic an L local geodesic?
Is every what?
Local geodesic an L local geodesic?
Yeah, L local geodesic means a local geodesic, I guess I mean L local for some L.
No, I mean the conventional definition of local geodesic, does it imply L local?
I don't understand the
Does
question.
the conventional definition of local geodesic imply L local geodesic?
I guess. Yeah, I don't know the conventional definition. I guess I know this definition. Okay, sorry. Yeah. I think there's like a definition in like Riemannian geometry of a local geodesic that does imply this. That is an example of this phenomenon. Yeah. Yeah, in like Riemannian geometry, if you have a path that satisfies like acceleration is equal to 0, then on a small neighborhood, oh maybe it doesn't apply this with a maybe not with a specific L. Okay, yeah, maybe not. geodesics in like Riemannian geometry sense, where the acceleration is 0, are locally geodesics. They're locally length minimizing, but maybe not for some uniform number L like this. So maybe this doesn't hold. Okay. Okay. But I care only about this definition, not about any other definitions of local geodesics that may have existed in the past. Okay. Okay. Oh yeah. So this fact. So is it clear what that means? So in particular, this is sort of bad behavior. Like I could extend this down to really close, and this would still be like a pi local geodesic. But look, at the end of the day, I'm getting really close, even though this is like 2 pi around, but these 2 points are really close to each other. So I'm kind of would be violating this, except for I have this additive error. Maybe it would be okay. But this is ruling out this sort of behavior. Does that make sense? All right, we'll see that coming up in a second. And yeah, maybe I was thinking I might try to prove that. But then I decided against it. But let me try to just give you one idea about why behind that fact. Okay. Okay, so one way you might try to prove that fact is to sort of prove it inductively for paths of longer and longer length, right? So that's clearly true for paths. If I look at L local geodesics, then they all satisfy the conclusion at the end if they're only L long. Okay, so now I might try to look at longer and longer paths with the same L local property and still get try to prove the same conclusion. Okay, so here's the picture. Let's try to do it for things of length 2L. Okay, so I have maybe my path like this, and let's suppose that this is length 2L and it's an L local geodesic. Okay, so now what I'll do is I'll break it up. I'll take the midpoint here. That's the midpoint, and then I'll draw an interval of length L around it. So it's a geodesic on that because that's of length L. Okay, and now I do that, and then I also draw the geodesic between the endpoints, which confusingly goes that way. That's okay. And then I also look at these sides, that and this thing over here. Okay, so now what I've drawn is a geodesic quadrilateral. Do you see it? There's 4 geodesics, right? The inside bit is length at most L, so it's geodesic. This is length like L over 2, so it's a geodesic. This is length L over 2, so it's a geodesic, and I chose the red to be a geodesic. Okay, so it's a basic fact that in hyperbolic spaces, geodesic quadrilaterals are 2 delta thin. Okay, meaning you have one. Each side is contained in the 2 delta neighborhood of the other 3. Okay, what's the proof? Just here, you pick your point on this side, draw the triangle that way. It's close to a point over here or over here. If it's over here, I win. Yay. Okay, if it's not over here, if it's a point over here, well, I still have to find a point on the other 2 sides that it's close to. But this triangle is delta thin. So this is close to a point over here or a point over here, delta, so I'm 2 delta away from that point. Okay? All right, so now let's apply that to my picture. All right, so this point is close to 2 delta close to something on the other 3 sides. Well, this whole half is a geodesic. And maybe I'll assume L is pretty big. Okay, so it's not close to any of these points because it's at least like L over 2 away, and L is pretty big. And it's not close to any of these points. Okay, but it's close to something. Where's the point it's close to? It has to be over here on the red guy. Okay, and this is at most 2 delta. Okay, so that means the length from here to here is roughly this length plus that length, minus 4 delta. Okay, so I'm proving the 2 endpoints are pretty far apart from each other in terms of the length of the path, which is what I was trying to do. Okay, and then you might imagine trying to extend this sort of inductively and not lose control of the constants. Okay, but I'm not going to do that. Okay, All right, okay, so that's great. I mean, hyperbolic spaces, maybe I could get behind, but local geodesics, what's that good for? So I went through all of that because I want to give the following consequence. Okay, so this implies, given a hyperbolic group, say with a finite generating set S, okay, then there exists some number r bigger than 0 such that if I have a word and the letters S is trivial in G. Okay, so you take an element of your group, you express it as a product of generators, as a word like this. Okay, and if I have a word like this and it's trivial in G, meaning that this defines the identity element, then there is a subword of W of length at most R that is not geodesic. By which I mean it can be shortened, can be replaced by a shorter word. Okay, does that make sense what I'm claiming? Maybe I'll draw a picture. Okay, so all right, so why? Well, we'll draw the picture and convince you that it's true. Okay, so the word gives you a path in the Cayley graph. Right, so here's the Cayley graph, and I start at the identity, and I start, reading S1, S2. This gives me some path, and it comes. The fact that it's trivial means my path comes back to the identity. Okay, that's what it means. Now, suppose the conclusion was false. I take R to be like the number L over there, pretty big. Okay, so suppose that the conclusion was false. That means that every subword of W of length at most R was geodesic, can't be shortened. That means this thing I've drawn would be an R local geodesic. Every subpath of length R is geodesic. Well, the fact means that the endpoints have to be far apart from each other. That's what it says. The distance from the first point to the last point is at least half n, it's at least n over k minus k. So if n is really big, I couldn't have come back because the distance between the first point and the last point is supposed to be far. Okay, so if the conclusion fails, this is a local geodesic. It's an R local geodesic, so can't be a loop. Okay, that's kind of the idea of local geodesics. They can't be loops like that. Does that make some sense? Nope. Okay, so this is great because this gives a fast solution to the word problem. Okay, so the word problem in a group is I have a group, and I pick a word in the generators, and then I ask you to tell me if it's the trivial word or not. And you're supposed to be an algorithm, right? So you're some algorithm to answer this question, yes or no, or is it the trivial word? And the thing is, my word might be really long, but you're supposed to tell me an answer quickly. Okay? So what's the algorithm? So given a word, look at subwords of length at most R and try to shorten. Okay? So maybe at the beginning of my algorithm, I list all possible words in my group of length 2r, and I record which ones are trivial. So then you give me a word. I check every subword of length r, and I want to know, well, is that the shortest possible word, to get between those two things? And if it, so how do I check that? I look at all of my words of length 2r that are trivial, and I see if this occurs as a subword of them. Okay? And if that is, then I can shorten my word and get some new thing. And then I repeat, and I just keep shortening at each step. So I only have to do that n times, right? So given my word n, I check all subwords of length at most r. There's like n of those. For each one, I check it against some finite list of trivial words. And if I find a shortening, I do that, and then I have a shorter word, and I again check, n times, or n minus 1 times, and then I shorten, I check n minus 1 times. And this algorithm either stops when I've reduced it to the trivial word, or at some stage of the algorithm, there are no shortenings. If there's no shortenings, then that means I'm non-trivial word. I can't shorten. Okay? So that's called Dane's algorithm. Okay? I didn't write that out all very carefully, but I hope the idea is somewhat clear just from what I said. Okay.
That would only shorten down to like r, right?
That's right. Yeah, so I'm assuming you first wrote down all possible words of length 2r and have a list of which ones are trivial. So if you shortened it to length at most r, then you already know whether or not you're trivial.
So n much bigger than r.
Yeah. Yeah.
So if I give you a hyperbolic group, you immediately figure out what r is?
Yeah, so this r basically, it goes back to this fact. So given the delta, I can come up with k and l. R is basically L. And this L is computable in terms of delta. So if you give me the hyperbolic group and tell me what delta is, then I could tell you what R is. Sure. And there's algorithms to check if a group's hyperbolic and to figure out what delta are and so on. OK. Similarly, you also get fast solution to the conjugacy problem. So the conjugacy problem is I give you two elements of the group, and you tell me whether or not they're conjugate to each other. And if so, you find a conjugator. And you can similarly use geometry to find a fast solution to this problem for hyperbolic groups. It's a little more involved, so I don't want to sketch it. Okay? So here we see this sort of geometric structure of the group is giving you, powerful algebraic information about the group, which is kind of amazing. Okay? So that's one reason to care. Maybe just one more thing before we go on. Which is just because it's cool. Okay, so let's let sigma n be the following thing. I look at all elements in my group such that the distance from the identity to G is is equal to n. Okay, so that's the sphere of radius n in my group. Okay, and then I take the number of such things. Okay, so the sigma n is just the number of things in the sphere of radius n. Okay, so I have all this list, and maybe the thing you care about in your group is you really want to know what these numbers are. Okay, in general, it probably seems hard to calculate what these numbers are, for a group, finally generated group. So, but the amazing thing for hyperbolic groups, in fact, due to Cannon, back in the 80s, is that the generating function so I take these numbers and I put them as the coefficients of a power series. Okay, I just do that. I can write down that power series that defines, that's something, and I might wonder what that is. But this turns out to be a rational function. So this power series is a rational function, meaning it has the form p of x over q of x for two finite length polynomials. Okay, so in some sense, this long infinite list of numbers, I have no idea what it is. It's really captured by the finite data here in these two polynomials, which is amazing. And in fact, this is equivalent to there's being a finite length linear recursion among these things. So you could calculate that finite length linear recursion and then just calculate these things recursively. And So that's, I don't know, I find that kind of amazing that this geometric property of hyperbolicity tells you that the growth of the spheres like behaves some very nice algebraic property. Okay. No, I don't. No, the converse is not also true. It's true that this thing being a rational function is equivalent to there being some finite length recursion here, but that could happen for other reasons besides. Is that right? Oh, okay. Yeah, or maybe it is. I guess I don't know, but I assume that it's not. Okay, so that's that's what I wanted to say about hyperbolic groups in general. So now let's try to, in the last maybe 10, 15 minutes here, turn our extension to group extensions, which is the thing I actually am interested in. So, group extensions. Okay, so group extension, what do I mean by that is just a short exact sequence of 3 groups. Okay, so I think of this as a way to kind of build a new group out of 2 old groups. You're given some groups K and gamma, and I combine them in some sort of way, and I build a new group G. Okay, and the basic question is, when can hyperbolicity of K and gamma imply hyperbolicity of the middle group G? All right, this is a basic thing. You have groups with some properties. You try to build new groups out of them. You wonder, are those properties preserved by that? Okay? And the answer is it clearly depends. So for example, I could have this group extension. So that just the sort of obvious maps that you would think of when I write this down, where this is projection onto, say, the second factor, and this is the inclusion into the first factor. So that's a short exact sequence. Z is a hyperbolic group. It's a free group, or its Cayley graph is a line, which is a tree. So these 2 groups are hyperbolic, but this group in the middle is not hyperbolic, right? So that's certainly a non-example, or an example of 2 hyperbolic groups where the extension is non-hyperbolic. Okay, so it depends on how you glue your groups together. So we have to have some way to kind of think about that. Okay, so this thing, short exact sequence, induces what we call a monodromy, which is a map or homomorphism from gamma to the outer automorphism group of the kernel. So remember, if you have a group, its outer automorphism group is just the usual automorphism group where I quotient out by inner automorphisms. Okay, so how is this map defined? I take something here, gamma. This is a short exact sequence, so this map is surjective. Okay, so I can choose a lift here, gamma tilde. And then this is a normal subgroup. Okay, so that means it's preserved under conjugation by everything. In particular, it's preserved under conjugation by this element. So I can conjugate this group by this, and that defines an automorphism of K. Now that automorphism is not well defined because I made a choice here. But if I make different choices, the resulting things differ by an inner automorphism. So I get a well-defined outer automorphism. Okay, so the map is I send gamma to conjugation by gamma tilde, which is a lift. Okay, and the thing I want to point out is that we need rho to be kind of complicated. For G to be hyperbolic. Okay, so what, I mean, I'm not going to define that, but what do I mean? So just an example. If there exists gamma and gamma, say, and k say infinite order, such that rho of gamma, so rho of gamma is an outer automorphism, so it acts on the set of conjugacy classes. So if it preserves the conjugacy class of k, so if this fixes the conjugacy class of k, then if I look in my group, if I take k and I take some lift of gamma and I look inside my group and I see what they generate, it's going to be just like this, because I'm acting kind of trivially. So I'm going to get a z plus z in there. Okay, so if that happens, then k gamma tilde is isomorphic to a z plus z sitting inside of my group. So I'm not hyperbolic. Okay, so under this sort of monodromy action, it has to be complicated in the sense that everything has to sort of move every k around a lot. Nothing can fix a k. Okay, so it has to be kind of complicated in that sense. Okay, so I want to give you some results along these lines about when such things could be hyperbolic and sort of how do you control how complicated it is. So let's look at k is equal to a surface group or a free group. This is sort of a reasonable thing to do because sort of some high power machinery in geometric group theory, this JSJ theory, implies that if I have this situation where these groups are hyperbolic and G is hyperbolic, then if k is torsion free, it turns out it has to be a free product of surface groups and free groups. So like sort of the most natural thing to look at turns out to be surface groups and free groups, which are the examples of hyperbolic groups we were thinking of before. So let's just focus on that case here. And let's first consider the case of a surface group. Okay, so let's say I have a short exact sequence like this. Okay, so then I know I get this map from gamma to out a pi 1 of s g. And there's an amazing fact about surface groups that their outer automorphism group is in fact basically the homeomorphism group up to isotopy. So the homeomorphism group of S, which is some topological group, this I mean the connected component of the identity, or the path component of the identity. So that's an isotopy is a path in homeo. So that's I'm dividing out by isotopy here. And this is the Dane-Nielsen-Baer theorem that this outer automorphism group is in fact equal to this quotient, which is called the mapping class group. And that's sort of, you should think that that's amazing, right? Here, every homeomorphism induces an automorphism of the thing. But the amazing thing is that every automorphism, in fact, comes from a homeomorphism. So that's sort of surprising. It's like I hand you an automorphism. Now you have to somehow build an actual homeomorphism of the surface that does that. And the proof uses actually hyperbolic geometry of the hyperbolic plane. It's a very cool fact. Anyway, so we're just going to use this without explaining it anymore. And what we need is a way to kind of measure how complicated this rho thing is. And I'm going to use this. Okay, so we need to measure, in some sense, how complicated rho is. Okay, so let's see. So gamma is acting by outer automorphisms on my surface group. Okay, so gamma acts on the set of conjugacy classes in my group. Right, because I'm acting by outer automorphism, so I permute the set of conjugacy classes. Now, a conjugacy class in the fundamental group corresponds to a free homotopy class of curves. Okay? Free homotopy classes of curves in my surface. Right? Elements correspond to based loops, or homotopy classes of based loops, and conjugacy classes correspond to unbased loops, so free homotopy classes. Okay, and let's define S to be the set of conjugacy classes that correspond to simple curves. Right, if I have a free homotopy class of curves on the surface, I can ask whether or not it has self-intersections. So by simple, I mean no self-intersections. And it's maybe not obvious, if you just say, I look at this set of conjugacy classes, it's not clear that my group gamma would preserve this set of conjugacy classes, because it could send one conjugacy class that corresponds to a simple curve. It could send it to another thing that corresponds to a non-simple curve. But that doesn't happen because of the Day-Nielsen-Baer theorem, because your automorphism actually comes from a homeomorphism, which preserves whether or not curves have intersections or not. So gamma acts on this set. Okay, so Day-Nielsen-Baer implies that gamma acts on that set S. Okay, so now I want to build a graph. Another simplicial graph. It's called the CS. So the vertex set is just this set of conjugacy classes. S, okay, this conjugacy class that correspond to simple curves. Okay, homotopy classes of simple curves. And I have an edge correspond to disjoint curves. Okay, so two conjugacy classes are joined by an edge if the free homotopy classes of curves they defined are disjoint from each other. Okay, up to homotopy. Okay, so gamma acts on this set, and it preserves this relation, because again, it's acted by homeomorphisms, which preserves disjointness by the Day-Nielsen-Baer theorem. Okay, so again, gamma acts on this thing by simplicial automorphisms. Okay, so now I can use this as a tool to kind of tell you what I mean by complicated, I guess, in the last couple minutes. Okay, so just a couple facts. So here's one sort of important theorem that I just want to mention. That this graph, I could again think of it as a metric space, as a path metric space. That this is an infinite diameter hyperbolic space. So it has thin triangles for some delta. Okay, so that's sort of useful. I mean, that is an important thing that's used in the proof of the thing I'm about to say, which is the following theorem. So the question, remember, was you're given an extension like this, and you want to know when is the group in the middle hyperbolic group. Okay, so here's an answer, an answer. So due to work of many people, Farb-Mosher, Kent-Leininger, and Hamenstädt, so I have, again, this is the setup. Okay, so then the group in the middle, G, is a hyperbolic group if and only if the orbit map from gamma to this thing, C of S. So remember, gamma, I get a map to the outer automorphism group that's acting on this thing. So gamma is acting on this metric space, and I could look at the orbit map, and I want that to be a QI embedding. Okay, which again meant that it sort of coarsely preserves distances up to additive and multiplicative error for some fixed constant. Okay, so that's some sort of measure of complexity. It's saying words, elements in gamma that are like far from the identity have to move curves a lot. They have to change conjugacy classes to be sort of very complicated to how they started with. Okay, so that's a great theorem, and I think really amazing characterization of this hyperbolicity of this extension group in terms of this sort of topological object for the surface called the curve complex. And maybe I won't even write it down, but in sort of work with Sam Taylor, we've been looking at a sort of analogous question for the other side of the story for free groups. And there, in that situation, there's a sort of analogous simplicial graph like this. And we have where the same theorem holds, except it's only one direction. It's not if and only if. It's like this. Okay, and in fact, the converse is false in that case. So that's the best you can do. All right, I'll stop there. Thank you for your time.
Questions for Spencer?
You mentioned briefly why I1SG and group are the right things or good things to look at. Can you say more about why those are the right things to look at?
Yeah, so there's this JSJ theory for hyperbolic groups developed by Celan and Rips, which just says that if you're going to have this situation where K, G, and gamma are infinite hyperbolic groups, the only option is for K here to be a free product of surface groups and free groups. And that's just, yeah, I guess I can't really say much about why that's true. It's some sort of complicated machinery that outputs that in this case. It's just the only option. So that sort of suggests that those are the two natural sort of groups to start looking at. And then next you should look at free products of them and then see what you can see.
Is there a natural way to assemble the pieces into the extension for the whole thing?
Yeah, I believe so. I mean, actually, I haven't thought about it so much. But like this, you get a canonical decomposition of this group as a free product of so things. And this sort of extension, the outer action has to respect that decomposition because it's canonical. So I think that means you should be able to assemble them in some sense. Yeah, I can't make a precise statement. Okay, yeah.
What's the curve complex for free groups?
Well, for free groups, there's several complexes that are analogous to the curve complex in the situation of free groups. So depending on how you think of curves in free groups. So a common thing is what's called the free factor complex, where the vertices are free factors of the free group. And then I have an edge if one free factor is contained in the other. The vertices are conjugacy classes of free factors, and one's contained in the other if there's containment up to conjugacy class. That's not the graph that makes this theorem work. Instead, we call it the cosurface graph. So the vertices are primitive elements of the primitive conjugacy classes in the free group. So an element of the free group is primitive if it can be made part of a basis. Okay? And so conjugacy classes such things. And then there's a condition about when two such conjugacy classes are joined by an edge. It's if you can realize your free group as the fundamental group of a once punctured surface in a way such that both curves are simple at the same time as the condition. And then you define that graph, and then you get sort of analogous theorem.
So since the hyperbolicity of the group makes certain computations simpler, that's a true statement, right?
Yeah.
This algorithm. Have uses been found of taking a non-hyperbolic group and, say, embedding it inside of a hyperbolic one, extending it to a hyperbolic one, and then making computations in the original?
Yeah, I mean, so in some sense, yes, in some sense, no. So if you have a group and you embed it in a hyperbolic group in a way that sort of respects the geometry in some sense, then it turns out your group would have had to be hyperbolic in the first place. And if you do it in some bad way, where it's distorted and it doesn't respect the geometry, then I don't think it helps you very much. But there is a lot of work involved in taking groups that aren't hyperbolic and sort of, instead of trying to embed them in hyperbolics, is sort of to find hyperbolic pieces inside of them and like realize it as some sort of combination in like some very vague sense of different hyperbolic pieces that interact with each other in controlled ways. And that's a very big topic of study.